喂喂喂，有吗？这是徐恩有吗？徐恩有吗？
喂喂喂，有听到吗？有吗？Test test test。有吗？有吗？有听到吗 ？OK，
Okay. Yeah. Okay. We fix the stereo system. So let's start today's introduction. Today we're gonna do the experiments about the MOSFET. And although we haven't learned it from the electronics class, we will test some simple characteristic about this device. Um, Okay, and the MOSFET has been sorted into two types of this device, and one of them is the enhancement type, and the other one is the depletion type. And we also gonna see a bigger about the CMOS, which is being fabricated with uh, a PMOS and an NMOS. Okay, and the first one, this is the enhancement type MOSFET. As we can see, we gonna have some simple introduction about the fabrication of this device. And we prepare a P-type of silicon substrate first, and then we diffuse two region, the N plus region from the P-type into the N-type semiconductor materials. And the gap between these two regions, we call it the channel region, and we also oxidize some uh, oxide layer, a oxide layer on the top of the channel region, and then we evaporate some metal as the electrode, and as we can see that these four ports are called the gate, source, and drain, and the body electrode. So this is how we induce the channel layer. We added a positive VGS voltage at the gate electrode, and we can see that the majority carriers in uh, the minority carrier in the p-type substrate will be attracted into the channel region, as we can see here. And so this is the induced N-type channel. The N-type channel will connect both source and drain region, the N plus region. And then as we have added a small voltage on the drain side, there will be a current flow through the channel region. And here is the child region that we call we added the very small BDS on the drain side and about 0. 0.1 to 0.2 volt. And the current is flowing from the source to the drain region, and in, it was conducted by the free electron. And the current ID is determined by the uh, electron concentration, and also being uh, determined by the VGS we added on the gate port. And as in the child region, the operation region of the device, the conductance of the channel is proportional to the gate region we added, the VGS minus VT. The VT is the threshold voltage, and the ID current also is proportional to the uh, voltage we added. So here are the current curves. As we can see, the ID to VDS, and the larger the VDS we add, the larger ID we get. So we can see these four different line as we measured after the different VDS we added to the device. And if we add the VDS larger and larger, and they will become the device will turn into the saturation region, and we can see that this is a pretty pretty much difference between the figure we see before, and the channel depth of the device near the drain side is shallower, and it's not a very uniform channel layer shape, and it will let the currents become different from the child region. So here is the ID to VDS. As we can see, the left hand side uh, is the device we operated in the child region, and the larger the VDS, the larger ID we get, and then it become it uh, increase more slowly, and then it come to the saturation region. It comes to the saturation region, and the current ID is maintained at the current at a constant value. So the ID is in the saturation region. We can represent it as the ID equals K to this uh, VGS minus VT, and uh, the edge of the child region and the saturation region is being determined by this voltage. And the left-hand figure is the equivalent circuits that we can see, which is represent the MOSFET device, and we can see that the gate port is separated from the other ports, and because it has a oxide layer under the gate port, and then the channel current we represented is this current source. So here are the same figure we have seen before. So okay, and then uh, the device has a characteristic which is similar to the BJT, but in this device we call it the channel length modulation effect. The channel length modulation effect, which means the larger VDS we add, the ID is not equals to a constant value. It will have a slow increment about it depends on how how large VDS you add, and we have to change the equation we wrote before, and it is related to the VDS as we can see in this equation. And also, which is similar to the BJT device, we added an resistance between the source and drain port, and this is the way uh, we simulate the channel length modulation effect. And here are the enhancement type MOSFET, the symbol of the enhancement type MOSFET. And we can see that both NMOS and PMOS have different arrow direction. And the arrow means the source port. This is the second part of the introduction. The device has a depletion type MOSFET. The depletion type MOSFET also have four different ports, but we didn't see the body port in in these two figures because the body port we always connected grounded, and we can see that it has the uh, similar structure as we saw in the enhancement type device. It has a gate electrode, which means the gate, and it also have the oxide layer and the source drain uh, region. But there is a physical and it exists between the source drain N channel. Even if we didn't add any VGS, there will be a current ID flow through the channel if we had a voltage added on the drain side. So the ID to VGS curve, it has a little bit shift, as we can see in this figure. That because even though we haven't add any VGS, there is a current ID, and the threshold voltage means the way the voltage you added on the gate port, and you will dispel the electron from the channel layer, and it will disappear. So here is the current equation of this depletion device, which is pretty much similar to the one we saw it before. And here are the four different devices, uh, which two of them is the enhancement type and two of them is the depletion type MOSFET. And we can see that NMOS and PMOS have different direction of these current curves. So sometimes we have designed the uh, circuits or some different application that we use both N-type and NMOS and PMOS device, and we fabricate it on the same wafer. So we can see that on the left hand side is an uh, and PMOS, and the right hand side is an NMOS. And so we combine these two devices and made it very close, and we connect the correct ports between each other. You will become a CMOS structure, and the CMOS structure which sometimes we use it as an inverter to change the input voltage from a high voltage to a low voltage. So this is the application we have used in the CMOS technology. So here are the today's experiments. We're gonna practice some parameters measurement about the MOSFET, and we will learn the simple characteristics about this device, and we will start today's experiments.